Well, hello, and welcome to our next video. I'm calling this video Specific Volume and H versus U. So let's start with specific volume. Somewhere along the way, we may have talked about what specific means in thermodynamics. And in thermodynamics, specific means per unit mass. And in thermodynamics, we use a lowercase letter. So I'm going to use a lowercase v. And I'm going to say, well, that's volume, capital V, divided by mass. So specific volume is volume divided by mass. Units, feet cubed per pound. Want to go a little metric on us? Meters cubed per kilogram. Does that look familiar? Feet cubed per pound mass. Volume per unit mass. Yeah, it kind of does. Kind of reminds me of density. What's density? I always just have it in my head. Mass per unit volume. Ah! Volume per unit mass, mass per unit volume. All specific volume is 1 over density. Having been in science classes for a long time, you've used density a lot. We have a sense of what density is. Density is how dense is something, how tightly packed are the molecules, which is more dense, lead or air. So there it is, specific volume. Who cares? Well, I care. So far in thermo, we have seen pressure times specific volume as a thing. What was that thing? Oh, it was flow work. In other words, how much energy it takes to move a fluid has to do with what pressure is being applied to the fluid and how dense is the fluid, or what's the specific volume of the fluid. So for some reason, when you take a fluids class, everything's done in density. When you take a thermal class, everything's done in specific volume. When we start going into the steam tables, we will see specific volume is listed. So specific volume is a thermal property. It's volume divided by mass. Let's put a box around that. We have units, feet cubed per pound or meters cubed per kilogram, and we see that it's useful in calculating the flow work done on water moving, so fluid moving, I guess not water, but any fluid that's moving. If you think about the vapor dome, and you've got a liquid on the left side of the vapor dome, and then you've got at boiling point 100% liquid, all the molecules as tightly packed as you can get them. And then you start breaking some of the bonds so the molecules are further apart. I think you would agree with me that as you move across the vapor dome, well, we've already identified that entropy is increasing, but I think you would also agree with me that specific volume is increasing as you move across the vapor dome. So it does allow us a way to sort of think about how the molecules are getting further apart, thinking about a phase change. So the volume has some value there as well. All right, that's part one, specific volume. Part two, H versus U. So in class, we have gotten to the point, well, let's go with the steady state. Let's go with the steady state rate, first law. So I want you to press pause and write the steady state rate first law. Did you write Q dot in minus Q dot out plus W dot on minus W dot by plus M dot in PE in KE in H in minus M dot out KE PE out KE out plus H out equals 0? Or some algebraically similar thing, maybe have all the ins and ons on the left and all the outs and bys on the right? Did you maybe say, oh, hey, this is thermal potential energy and kinetic energy are almost always negligible? Cool. That would be fine with me. Let's say that we had a boiler. And in our boiler, there is no heat transfer out of the fluid, no work on, no work by, and we're left with Q dot in the boiler equals M dot of the steady state. So in and out are going to be the same. M dot H in, oops, move it to the other side, H out minus H in. It's worth remembering, yes, that is the equation for a boiler. But it's worth remembering what H is. Enthalpy is a convenient grouping of U plus PV. Internal energy plus pressure times specific volume. When you have a boiler, you bring the water in, it's usually a liquid, and you take the steam out, it's usually a vapor. You ask yourself the question, is U changing? Are the molecules moving faster or do they have more energy? And the answer to that is yes. Then you say, are P and V changing? Well, we haven't talked much about it yet, but P doesn't change a whole lot in a boiler. But does V? Does the specific volume change in a boiler? Yeah, it goes from a liquid to a vapor. So it's not just the internal energy that's changing in a boiler, it's also the flow work, the PV. They are changing. So in a boiler, or any place you have a phase change, it is very important that we use H. Let's take a look at another example. How about a heat exchanger? And in our heat exchanger, we have a coil, copper wire, or copper piping, and we are going to have liquid enter at point 1 and liquid leave at point 2. Very common in a heat exchanger. And it doesn't matter whether we're exchanging the heat from this being the hot fluid to another cold fluid, or from a hot fluid to our colder fluid. Doesn't matter. What would the steady state, let's say that we have heat coming in, what would the steady state first law look like for the heat coming into the water, liquid water, in this pipe? And very quickly you're going to tell me Q dot in equals M dot of this water times H2 minus H1. And you are right. But if H is P2 V2 plus U2 minus P1 V1 plus U1. That's what H is. H2 is U plus P2 V2. H1 is U plus P1 V1. The question is, if it's liquid and its pressure is staying the same, or very close to the same, and it's not changing its density or its specific volume, whatever pressure and volume it came in at is the same pressure and volume that it leaves at. So whatever pressure and volume it came in is the same pressure and volume that it leaves, and these two end up canceling out. So there are times, especially when you have a liquid not going through a phase change and not having its pressure change very much, that delta H is really the same as delta U. Absolutely not true in a phase change. Can be true when you don't have a phase change. Can be true if you have air and you're not changing its pressure or density. So you will, as you go through your thermodynamic life, in my thermodynamic life, I go through it always looking at H. But when you read different things, you're going to see some places that you have rate of heat transfer equals mass flow rate times delta U. And you'll, when I see it, I scratch my head and say, why on earth are they doing that? And then I realize, oh, they're doing delta H, but PV is staying constant. That's the approach that I take. All right, well, thank you for joining me for specific volume and U versus H. Hope you have a great day, night, whatever. Always wear your safety glasses.